In this video, I want to talk about functions and different ways we can represent functions and how to tell something is a function. The main thing that defines a function, for every input corresponds to exactly one output. So the idea of a function is we're going to be inputting things, applying some rule, and getting an output. But every single input needs to have exactly one output. So let's look at different ways to represent this and how to tell something is either a function or not a function depending on the representation. One way to represent a function is just a list of ordered pairs like this here. In this case, our inputs, I'll go ahead and shade. These are the first coordinates, the 2, the 3, the 4, and the 5. The outputs, I will underline. That's the 3, 7, -1, and 2. So this is a function because every single input has exactly one output. We can see that for everything I input, I get a single output as a result. Here's another example of a list of ordered pairs. And if I highlight my inputs, I can see that they are 1, 2, 0, and 1. And I can tell right now that this is not a function. In particular, I have an input that does not have exactly one output, it has 2. Inputting 1 gives me an output of 7 as well as an output of 1. So in this case, whenever I list my ordered pairs, whether they're in this form, or I could have also listed these in a table like this, the main thing is the inputs, the first coordinates, the x values, need to all be different. In this case, I have some repeats in the first coordinate, so not a function. One more example. In this case, I can see my repeats in the outputs. My inputs are all different, 1, 2, 3, and 4, but my outputs are all the same. And that's perfectly allowed, so this is still a function. As long as the inputs are all different, it is a function. Here's another way to represent a function. We have our inputs in one oval, our outputs in the other, and we just draw arrows. If I input 1, I output 6. If I input 2, I output 8. Inputting 3 will output 5. Inputting 4 outputs 7. So this is an example of a function. Here's another example, and this one has two strange things happening here. First off, this 1 and 4. For 1, both an input of -1 gives me an output of 1, and an input of 1 gives me an output of 1. An input of both -2 and 2 gives me an output of 4. But this is fine, as long as each input corresponds to exactly one output. The other weird thing is this 2 and 3, that nothing outputs to that. No matter what I input, I do not get 2 or 3 as an output. And that's also perfectly fine. We can do lots of weird things over in the outputs. This is still a function. So what can violate functions using this method of representing a function? Here's the first thing that could go wrong. In this case, every input is corresponding to not one output, but 2, and that's not allowed. So essentially, when I look at these arrows, I can have multiple arrows going to the same number, but I can't have multiple arrows coming from the same number. Each one of these should only have one arrow coming from it, although we can do lots of weird stuff in the outputs. Another example of what could go wrong, here we can see that 5 does not have an arrow coming out of it, which makes it not a function. Each input should correspond to exactly one output, and here I have an input that does not correspond to an output. We can have extra stuff in the outputs, but not in the inputs. Another way to represent functions is their graphs. And for the graphs, we use what's known as the vertical line test. Here I have a graph, and I want to know, is this a function? The idea of the vertical line test says if I draw a vertical line anywhere on this graph, it does not intersect it more than once. So here I can see this vertical line intersects once. This one also intersects once. If I draw a vertical line here, it'll intersect the graph once. So this would be an example of something that is a function. If I look at this one, if I draw a vertical line here, it'll intersect my graph once. If I draw it over here, it intersects once. However, if I draw it over here, it doesn't intersect at all, and that's perfectly fine. This is still a function because it can't intersect more than once, but one or fewer is perfectly fine. Now let's look at this graph. If I draw a vertical line over here, I can see that it intersects the graph once. However, if I draw a vertical line here, it's going to intersect twice. Here, we actually intersect 4 times. So this is an example of something that is not a function because there are vertical lines that intersect this graph more than once. Another way to represent functions is through equations. Things like y equal to 4x plus 8, or 2x squared minus 7y equal to 9. And these are allowed. I'm not going to go into details about this too much, but in order to be a function, I need to be able to write it as y equal to something, and this something needs to be unique. So as an example, this one has y equal to 4x plus 8. That's allowed. This one, I could write it, and like I said, I won't go into details right now. 2 over 7 x squared minus 9 over 7. However, if I had something like x squared minus y squared equal to 0, I won't go into the details on this now, but we could write this if we tried. It would be y equal to plus or minus the square root of x squared, or y equal to plus or minus x. And this is going to cause an issue because this is not unique. If I input a number, I get 2 outputs, a positive and a negative one. So this is a little bit more tricky, and I won't go into too many details here, but this is another way to represent a function, is through an equation of the form y equal to something unique.